Hey everyone. Hope we're off to a good start or end to a Wednesday, depending on your time zone. If you've been part of the prior Lightning lessons, this one's going to go a bit differently. I don't have a local Slurm cluster anymore, so I can't sit here and run stuff for you. Instead, it's going to be more of an educational talk on what is Slurm, how does it do the things that it does, and then we're going to borrow some code from Stas Beckman's ML engineering book, because in my opinion, it does an excellent job of giving just bare bone examples of Slurm, what the certain formatting looks like, how you run things, how they're called. And it's really a book that if you're wanting to do ML engineering and get good at, what it takes to run things at scale, like what the course is teaching, what these Lightning lessons are sort of on about, it's an excellent way to learn about what that is from the hardware perspective. And so, like, what are flops? How do you measure flop utilization? How do you orchestrate all this stuff? How do you run redundancies? It's really an excellent one-stop shop for learning these techniques, which I will go ahead and drop in the chat now for everyone to have access to, and there will be a link to it afterwards as well. That'll go out through the handout. But let's get started. So, what is Slurm? The general idea is, let's say I'm running on my local PC that has 8 GPUs, right? So it's one computer on 8 GPUs. Well, for running any sort of script where I want to utilize all 8 of those GPUs, I could do something like torch run my script.py, or I could do deep speed my script.py. These are Python interfaces that run your script on essentially 8 separate processes, with each process correlating to one of your GPU IDs. That's fine. That's easy at scale of one node. Problem is when you expand to 2+ nodes, because there's a few things that have to happen. The first thing that has to happen is, let's say we're using torch run, which is torch.distributed.run. It is what they call an elastic launcher that runs all this setup. In order for multi-node to work with torch run, essentially you have a set of configuration. So it's like torch run nproc per node 8 and nodes 2. The command is essentially rank. And so what this says, if we translate, it's I'm going to run torch run, which is going to have 8 GPUs per node running on 2 nodes. Now this rank, you specify as either rank 0, rank 1, rank 2, rank 3. And this is overall what is the main computer facilitating everything, and who are the child computers or nodes that are running everything else, right? So rank 0 will be sort of the centralized zone for all of the communications. Now, as you can might imagine, the first thing I just said there gets a little weird. This command needs to be ran on every machine, because along with rank, there is also main process IP as well as main process port, right? So this would be the location via TCP of where the original node lives. Well, problem A you run into here is this command needs to be ran on every single machine. Well, if it needs to be ran on every single machine, that means every single machine needs to have the same script. And if every machine needs to have the same script, it all needs to have the same localized data. You can do that, right? I could have 2 computers with 3060s upstairs where I have 2 hard drives on each of them where they map to the same data. That's complicated and difficult and non-trivial. So we get through that by essentially storing the data in what is called like an SMP, essentially, or SMB, or a network storage device, essentially. Network storage bridge, I believe, is what the real terminology is. And essentially what that says is on every machine, I'm going to go to location, it's like / location / myscript.py. So we do this in our torch run command. So we would do something like torch run nproc in the script location. And now we have one source of truth for everything, for the data, for the training script, for where the model weights get saved. And in a sense, this is sort of orchestration, which is the idea behind what Slurm does in Kubernetes and everything else. We orchestrate a singular script or a process or a job to be ran across 1,000 different computers with the same setup when it comes to localized storage, the exact same topology when it comes to GPU count, especially for whenever we're trying to do distributed training, ideally CPU count as well. And essentially, everyone is clones of each other. Or replicants is really what we call them. This way, we essentially are making many machines act as one big machine, right? So if we think about torch distributed, typically whenever you're doing the zero algorithm or fully sharded data parallelism, the aim is to make multiple GPUs act like one machine. Orchestration and how that applies to machine learning operates in the same fashion. You don't per se split the model across all the computers because there's time that it takes for like gradients to be sent from one computer to another. Now, some of the guest speakers in my upcoming course actually talk about how they do that at a worldwide scale. But for the sake of Slurm, we're talking specifically about computers that have the exact same topology, the exact same data, because they're all on this network storage. And they're all being ran from one command or one orchestrator. So what do I mean by this? Earlier, we talked about how in order to run torch run, I need to run on every computer. With deep speed, that's a little different. You can do multi-node on deep speed using deep speed my script and just specify in a deep speed config what the topology is and how every computer is located. This requires that every single machine is set up for passwordless SSH between them all, essentially. If you're running on 4 nodes, maybe 8 that you locally own, that's reasonable enough. When you just want something to run and you have 1,000 nodes, each with 8 GPUs, setting up passwordless SSH and remembering everyone's IPs and whatnot is just unfeasible. And so this is where Slurm comes in. Slurm is essentially a wrapper that says, okay, I have a cluster with 1,000 nodes, right? 1,000 different computers that I'm storing in a database somewhere. And I'm going to create, well, the user is going to create configurations through a bash command that let me select what GPUs from this cluster I want to use, and then I'll go do this replicant nonsense on all of those GPUs because everything is set up exactly the same, because that's how it works. In my case, I set up Slurm locally to just learn it. I set up 4 Raspberry Pis and 2 computers with GPUs because Slurm, you call jobs based on resource allocation, which I'll show examples of this in a moment. But basically, I can sit there and specify like, okay, let's say I have a single node of 8 GPUs. I'm going to use Slurm, tell it I want 2 GPUs from this. It'll go look at what everyone's using, first of all, and then it'll go, okay, well, John is using 6 of the GPUs on this machine, but Alex only wants 2 of them. Okay, We'll give Alex these two, automatically allocate it, give him a dedicated job. No one can interrupt him, and off you go. Each of you are using separate resource allocations by yourselves. This is the other useful thing about Slurm. It is based on the idea of jobs. Everyone has specific resource allocations, and you don't step on each other's feet. Really handy for researchers who like to just go run scripts and just be done with it, and you're trying to work with a team of like 20 people trying to organize everyone using 100 GPUs. That gets real messy real quickly. Now, let's look at sort of what that takes. Here I have the chapter from Stas's wonderful book on launchers. And essentially, there's some examples in here that show what torch run looks like when using Slurm, the accelerate launch command, the lightning command, and then srun, which we'll talk about srun in a bit. For right now, we're going to focus on the examples that are torch run and accelerate. So let's look at the torch run. Now it's going to be some weird comments, and we'll break it down line by line. So when you run things via Slurm, you run a command called srun, and then you pass it either the bash file to use or a certain configuration. Now, specifically, what this bash file needs to state is some configuration parameters. So in this case, we have these parameters are denoted by sbatch in a comment line. In here, you'll state things that are easy to look at whenever you're looking at what everyone's doing. So you specify a job name, the number of nodes you want, the number of computers, the number of tasks per node. This is how many times it's going to be running on each node. We don't want to run things that are designed for multiple GPUs on 8 GPUs specifically to be run 16 times. We'll hit issues, right? Because we're going to be trying to address GPUs that already have addresses and are already running off of the 8 replicants already happening. So we set a single task per node. Really what these 4 here help with, so we have nodes, tasks, CPU cores per task, and then Gres, which is the GPU topology. So it's per node, right? These specifically are per node. What this helps isolate is, let's say I have a Slurm cluster where I'm not running replicants of everything, right? The hard drives are all running replicants, but the actual GPU topologies vary immensely. I have some H100s, some A100s, and then we're piggybacking off of one of our employees' 4090 set of 8 clusters. Well, you can specify, you can even get more specific in Gres here, what GPUs you want to use down to the hardware level. So using this configuration, I can specify use 2 H100s or use 2 4090s. In general, as a good practice, you should specify a timeout. This means how long it's going to take. In that way, you're not running for infinite. And let's say you're hit a timeout issue, your other coworkers aren't sitting there waiting for the node to open and it ended early because we found an error. Exclusive means that people can't piggyback off your node. One of the things with, well, specifically, that means that you are exclusively using that computer. Generally, you don't want to do this unless you're using everything on that machine. And then partition is, you can run mini clusters in a cluster. So when I described having a cluster that has H100s, A100s, and 4090s, right? So we can define one as the 4090 cluster, one as the H100 cluster, and one as the A100 cluster. This helps us determine what we're using for them. Now, the other important part is having an output file, because this is going to be running. You are not going to be interacting with it. Essentially, it will start the script and then immediately end the terminal connection. And then it's just running in the background. So if you have no way to run it, you're running headless. Now, Stas's script here has a lot of setup, but the important thing that I want to get to is the Python chunk. How do you actually call torch.distributed.run or accelerate launch when dealing with this? The first thing that you need to do is specify how many GPUs per nodes and how many nodes. Typically, this is done through environment variables. Now, Slurm creates a bunch of special little variables for you in the environment to help you do stuff like this. This will be things like Slurm job node list and Slurm end nodes, which as end node sounds like, when you say spawn on 2 nodes, that'll return 2. So it keeps track of this stuff. Otherwise, you're in charge of remembering these variables and running it every time, which we don't want to do, right? We want to make our lives as easy as possible for using these big clusters or even small clusters. Then we need to define where that node 0 address port is, right? Where all the TCP connections are going to filter through and what's orchestrating everything. You can use the scontrol command to go ahead and get you the master address from everyone, right? I don't need to sit there and remember, oh, this particular address exists on this node, and I want that one to be my head, and so I'm going to save that somewhere. You don't need that anymore. Slurm handles that for you. Then for the launcher, we call torch.distributed.run, passing in the number of GPUs per node, the number of nodes, the node rank, which is another fancy Slurm protocol that we get, or environment variable, the address for the master port, the backend we want to use, and we're on our way. So then we can call that later using srun. So remember how I said srun is how you launch the jobs? You can either run it yourself or you can run it through a Slurm bash command, essentially, or a bash script, which is what's done here. So you call srun, you can give it some configuration. Wait is how long is the node going to remain idle before we free up that space. So that's, let's say someone's running a script and it's running for ages, like I mentioned earlier. This is how you specify, I want it to run for 60 seconds. If it's not doing anything and nothing's happening, kill the job. On top of that, if one node, if one GPU, anything has some error that it gives, but the rest maybe are going, kill it. Because that's an error that's happening on one GPU that could have been a GPU died. I want to stop the entire job. And then job ID is just an easy way for you to identify what that looks like from the Slurm configuration page. And then you just call Slurm. So in a nutshell, this is how Slurm gets configured. It helps you sit there and filter through a giant cluster of nodes and make it to where you're not sitting there and, okay, John's using ABC because he posted in Slack. Let me go use D, E, and F. Instead, it handles the grabbing of resources for you while also being a completely free platform, right? The pros of this is it's very customizable. I'm going to rephrase that a bit because some people would say no. The cons of this is you have to run it yourself, right? You need to be managing your own Slurm cluster, or someone needs to be, and have this infrastructure in place for this to work. The pro, though, is it's free. It's 100% free and I believe open source, and there's no overhead. It is just simply Linux, right? It's the Linux ideas of jobs and things like that. On the flip side, you have platforms dedicated to this, like Kubernetes. My personal opinion is if you can have the infrastructure in place to do it yourself, do. Because otherwise, you're kind of in a vendor-locked position, right? Where, okay, well, we need to use Kubernetes. Now I need to go hire someone that got trained in Kubernetes to go manage our Kubernetes cluster, and he sits there and looks at logs all day. Versus having one of your engineers that's good at Linux coding, for instance, do a crash course on Slurm, set it up, and then he can go sit there and do trainings along with everyone else. Now that's more full stack dev when you think about it, and you're adding, some weight to what he's doing, but that's not unreasonable. Again, I've ran my own cluster over here in my house for over a year before it just wasn't a pet project of mine anymore. It can be done, and it doesn't take a lot of experience to get there. So that's the big pros and cons, in my opinion, and why sort of I tend to gear towards things that aren't vendor locked, because it makes it more accessible to everyone rather than things that are. To go look at another example, if we're using srun, I believe this is, yeah. So srun in this case is a very simple script that focuses less on setting up everything we were doing before, right? We're not even using like torch run or anything. In this case, instead, we're focusing on the minimum bits needed to just call srun and do a script. In this case, it involves saving environment variables for Python to know what to use. When it's doing distributed training, it cares about what the local rank is and the rank, and then it'll do everything else for you. In general, this is sort of what my experience has been when using a cluster, because I used the Hugging Face Science cluster when I was actively working at Hugging Face on distributed training projects like that. And in my opinion, it's better. Like with Kubernetes and specific platforms, you'll get more thorough dashboards of usage and how everything's doing. But A, you could also make your own dashboards, and B, I don't know, dashboards are handy for identifying problems, but also don't need to be super thorough. Like even when I was investigating recently on like GCP how my distributed training script was going, there's a dashboard. I was looking at the dashboard. I only cared about 2 or 3 of the charts out of like the 1,000 of them. So it's a lot of noise. And if you don't know how to filter that noise, well, then you're staring at a bunch of charts that don't make sense. I know it's kind of a cop-out answer, but I don't know, that matters. The more time it takes for you to set up and do things, the less likely you are to do it again. Right? Or let alone the less time you're going to sit there and do it. Now, the only other thing I will say about how Slurm's topology is set up is typically you will have a host node, and then you will have subsequent clusters, as they're called. Now, the host node is what the true orchestrator is. So whenever we're sitting there and running our srun command XYZ, Slurm looks at our cluster, sends this to the host node. Host node sees what it wants to do, and then sends it off to the subsequent clusters of nodes. This doesn't mean that you need a dedicated node for doing that. This is just a Python process, right? It's not, well, not a Python process, it's a script, right? It's not actively using GPUs, it's just a filterer. So it doesn't actively need to have a bunch of free space going on. So the host node could technically be part of a subsequent cluster, and you could call it. That's not common practice, but you could. And that's sort of a TLDR of how Slurm works at a high level. I really recommend checking out Stas's book for more in-depth. The only difficult part with Slurm and why I sort of went to Stas's book in the first place is unless you have a cluster to play with, I'm really just chatting about ideas, which is fine, but it's not ideal. It's an important concept when it comes to distributed training, though, because you will get, if you're serious about this, you join a lab or something, you'll get access to a node and you're expected to know how to use it. And a lot of that will come with getting up to speed with what Slurm is. So even if you just walk away with this going, okay, so Slurm basically just makes it to where I can run torch run on all my computers and it'll magically allocate it for me and everything works. That's fine. That's really what I want you to get out of this. It's just understanding the landscape of how do things change when we go from Python run my script to Slurm bash command go run my script, and sort of the level of effort that's needed. Because to a certain point, Slurm isn't needed, right? If you have, say, 8 nodes that are shared between a group of people and no one's trying to fight for resources or anything, Slurm kind of can be a bit much, right? You could probably figure out the resource management on your own. Everyone quickly into the GPUs and sees what's used and what's not, especially if they're like rapid fire jobs that finish in an hour or two. But when, say, you've got a team of 20 or 30 people trying to share those GPUs, you need something like an orchestrator, because more likely than not, those GPUs should be running 24/7 with everyone's experiments. And specifically, what Slurm does is, let's say I run srun using cluster A 8 GPUs, right? Just pseudocode. And let's say I run 5 jobs on this. Well, if we didn't have Slurm and we're fighting for resources like we are now, this script passes, these fail, but also this one could wind up using the rest of the GPU memory, and then this script could out of memories. That's not ideal, right? We want this one to run until its completion, and then these ones fail. Well, the other important part when it comes to collaborative launching that Slurm will do is it will sit there and make a queuing system. So this one will run first, and this one, and then this one, and then this one, and then this one, with milliseconds of time between them run automatically. So you don't need to sit there and babysit and eyeball the GPUs and wait for one to open. You just start the bash script, it hits the queuing system, you can see where you are in the queue. The command is literally sq. You can filter by like the job name and whatnot. And just be on your way. You can go work on other things, you can come up with more experiments, set up more things to queue. Everyone waits in a line, and everyone has their spot in line. And then when it's your turn, you're not fighting to get back to the computer and like, oh God, I have 2 hours now to go use this thing, I better go do it. It just runs the script for you, runs the job, and you're on your way. So that is sort of my brain tangent on Slurm and why it's useful, especially as distributed training is everywhere now. Understanding, even at a high level, how these job orchestration frameworks work is sort of needed, right? Because you're dealing with thousands of users potentially doing stuff, especially if you're thinking like the global planetary stuff. You have a lot of GPUs to go through, a lot of users or coworkers that are trying to use them. And so there comes a tipping point when orchestration jobs like this are needed to just keep everyone sane. Now, we're about at 11:30, so there's 15 minutes for questions. Feel free to shoot any you have in there. This is very much so more computer science than it is, machine learning. Next week's lecture will be a lot more fun. We're going to talk at a high level of what the distributed pipeline, like what is pipeline parallelism, what is tensor parallelism, at a super high level, what these fancy terms mean. There's, half a dozen or so different algorithms at this point. Like, I was looking the other day and it's like, now we went from pipeline parallelism to tensor parallelism. So we have PP and DP to loco and diloco and bits like that. Landscape of acronyms has exponentially grown. So next week, we're going to talk a bit more about what each of those are at a high level, how they work, as well as some general advice on when to use them. But otherwise, I don't particularly see any questions, and that's all right. So after this, I will get the recording up, do a little bit of editing, and send you guys a TLDR of sort of what we learned, as well as some resources from Stas's book and the Linux documentation on Slurm. And I'll try and go find a YouTube video or two that sort of shows the setup. Good practice to sit there and try and do it yourself is get, 4 or 5 Raspberry Pis and try and set it up locally.